Alright, so here we go with our final lesson on actually graphing rational functions. So today what we're going to do is we're going to take a look at situations where the degree of the numerator is greater than the degree of the denominator. Now we've talked about this a lot and we do know some rules about that, but we're going to start off with this warm-up and then we're actually getting into graphing one of these guys here. So it says divide the numerator by the denominator. I've got two options here. I can either do long division or synthetic division in order to get this done. I'm going to choose synthetic just because it's faster and easier. So I'm going to do x plus 3 equal to 0. So whenever I do synthetic, I need to make sure that I'm using the solution to the factor in the denominator, not the actual factor itself. I'm going to list the coefficients of the numerator here. That would be 1 from the x squared, 1 from the x, and negative 2 from the constant. And here we go. Drop down the 1. Negative 3 times 1 is negative 3. Add down the column, you get negative 2. Negative 3 times negative 2 is positive 6. Drop down the column. This is my remainder right here. Alright? This is my remainder. So if I was writing this out as a result, a product, I would have a factor of x plus 3, because that's what we divided by. And then what's left is, because I started with x squared divided by x is just 1x minus 2. And then we have this remainder, so that remainder is going to be plus 4 over our divisor of x plus 3. So that's what that would look like if we were to divide out and factor and write an answer as a product. Okay? So some real quick things we're going to review here before we get in. Rational function is just two polynomials that are being divided. The vertical asymptote comes from setting the denominator portion of that polynomial equal to 0. Oops, 0. Okay, we've been over and over these rules, but alright, if the degree of the p of x, this is your numerator, the degree of the numerator is less than the degree of the denominator, then we have a line y equals 0 for the horizontal asymptote. If the degree of the numerator, p of x, is equal to the degree of q of x, then the line y equals a over b is your horizontal asymptotes, where a and b are the leading coefficients. In today's case, if the degree of the numerator is greater than the degree of the denominator, then f of x has no horizontal asymptote. Alright? This type of rational function has a slant asymptote. Now, I do need to make one correction on this, sort of, and that is if the degree of the numerator, p of x, is 1 degree. Okay? So is 1 degree greater than the degree of q of x, then we have a slant asymptote. Alright? And that's the only case we're going to deal with, our slant asymptotes. So, and we'll talk more about that when we get to doing the examples here. Holes in the graph. We've talked about holes if p of x and q of x have a common factor. Alright? Of x minus r, then f of x has a hole at x equals r, or the point value for that would be r comma f of r, whatever you get when you plug in f of r. To find these slant asymptotes, when the numerator has a degree greater than the denominator, you can use long or synthetic division, that's the reason for the warm-up, to find the slant asymptote. Alright, so let's take a look at our first example here. Okay, so it says, given the function f of x equals x squared minus 5x plus 6, we're going to go ahead and begin just the way we normally would. First of all, I notice that because the degree of the numerator is greater than the denominator, there is no horizontal asymptote. Okay? So the next thing I want to do is I want to check for vertical asymptotes and holes. Okay, so before I do anything else, before I do any division, I want to make sure that this thing doesn't have any holes in it, and so I'm going to start off by actually factoring the numerator here. Alright, so if I factor f of x, I get f of x equals numerator, let's see here, x minus 2 times x minus 3 all over x minus 1. So right away I know that there's no holes, so I don't have to worry about holes in here. But I do have a vertical asymptote then at x equals positive 1. Alright? So now that I know I have a vertical asymptote, I'm actually going to go back and I'm going to find and graph the slant asymptote of f of x. Now, in order to do that, I actually need to divide the numerator by the denominator. And again, you can use long or synthetic division. So I'm going with synthetic. X minus 1 equal to 0. So I'm going to divide by x equals positive 1. List my coefficients: 1, negative 5, positive 6. And my remainder. So drop down the 1. 1 times 1 is 1. Add them up down the column, you get negative 4. 1 times negative 4 is negative 4, and I get a remainder of 2. So here's the nice thing. When I'm finding a slant asymptote, I don't worry about the remainder. I get to drop this guy off. Drop remainder. I don't care about that in terms of where my slant asymptote is at. So what happens here, as you can see, I divided an x squared by an x, so I have x minus 4 left over. And so I now have a slant asymptote. Okay, so asymptotes, when we think about them, we typically think about them as straight lines. They don't have to be, but everything we deal with will be. So my slant asymptote, A-S-Y-M-P, we're just going to leave it like that, is now y equals x minus 4. That's a linear equation. That is now my asymptote. No horizontal, I still have vertical, but now I have a slant asymptote at y equals negative 4. So I'm going to start off by graphing the vertical asymptote. So we're going to go back to red here. We've got one vertical at x equals 1. So I'm just going to come down and graph that. That's still my undefined portion of this graph. I'm going to graph the slant asymptote at y equals x minus 4. So this is just negative 4 with a slope of 1 to 1. And because this is a slant asymptote and I need a pretty good idea of where my graph's going, I'm just going to go ahead and graph a whole bunch of points. Alright, just like that. And now I'm going to finish this off just like I normally would. I'm going to find the x-intercepts, the y-intercept, and then I'm going to find a couple points on either side of the vertical asymptote if I need to. Alright? So, let's keep going, because everything else now is exactly the same as what it was. X-intercepts. Alright? So, to find x-intercepts, I need to set y equal to 0. Alright? My function was x squared minus 5x plus 6, and this was over x minus 1. Now, if you remember from our other talks, the x-intercepts always come out of the numerator. When I go to cross multiply, that denominator cancels out, and I end up with 0 equals x squared minus 5x plus 6. And now I need to solve that. Well, here's the nice thing. We already factored this up above. So we already know what the factors are. We have x minus 2 times x minus 3. So it looks like we have two x-intercepts here. One at x equals 2, one at x equals 3. And so I'm going to graph the point 2, 0 and the point 3, 0. Alright? So I'm going to come over here and do that. Now this looks kind of weird because they're both sitting on the x-axis there, and You know, we can't go straight across there, but that's okay. We'll sketch it in a minute. Y-intercept here, we're going to plug in, this is f of 0. All right. Now, if you take a look at my function, again, I'll do the math, but the y-intercept should be the easiest one. Well, actually, I'm not going to do all the math, because if you look to the left here, 0 squared is 0, 5 times 0 is 0, all that's left in the numerator is 6. On the bottom, you get 0 take away 1, which is negative 1. And so you have a y-intercept at 0, negative 6. So I'm going to come down here and graph that guy down there. All right. Now, just to kind of let you see what's going on today, I'll do a couple other points. But again, once you get used to these, you might not have to do any more points. So, for instance, I don't know, maybe I'll choose to do, I'm going to do my t-table right here, x and y. All right. So if I look at my graph, I've got a point right next to the asymptote at 0. I might try like negative 1 in here, maybe even a negative 2 in here. And then to the right side of the asymptote, I might try one, say, around 4. All right? So if you plug these into your equation, at negative 1, you get negative 6. At negative 2, you get negative 6 2/3. And at positive 4, you get 2/3. All right? So I'm going to graph those. So negative 1, negative 1, negative 6. Look at this. These two guys, they line up right next to each other again. Isn't that kind of weird? But at negative 2, we're down just a little bit further here. So you can start to see the graph dropping down next to that slanted asymptote. Okay? And then 4, we're at 2/3. We're right up here. So you can see the graph up top on the right-hand side, again, slanting out towards that asymptote. Now, we know about asymptotes. We know that vertical asymptotes, as I approach a vertical asymptote, I'm going to go up towards infinity on the right side here. As I approach the slant asymptote, I'm going to approach just like this. And I cannot go straight across the x-axis here. So there has to be some sort of a little loop-de-doop down below here. All right? If I went straight across the x-axis, then I should have been able to find more x-intercepts than I have. So going to the left side, I would do the same thing. My graph is going to curve down towards the vertical asymptote. It's going to curve out towards the slanted asymptote. And I've got to have some sort of a curve between those points up there. It cannot go flat across. And there's your graph. That's a slanted asymptote graph. That wasn't too bad, was it? That was actually pretty easy, huh? All right. We'll do one more here. So number 1, I want to factor h of x. You know what? In this case, you can factor it, but it's just x minus 1 times x plus 1 all over x. You can see that there's no holes. Nothing's going to cancel out, so I don't have to worry about holes on this guy. So my vertical asymptote, again, comes from the denominator. I take the denominator and I set it equal to 0. I have no holes, so I don't have to worry about any of those guys. Find and graph the slant asymptote. Now, this is an interesting division here. Okay, and you can still do this with synthetic division. So I'm going to take my denominator. I'm going to take x equal to 0. Now normally it's x equals 2 or x equals negative 3 or whatever it is, but this time it's 0. I'm going to set up my synthetic division just like I normally would. So I start with 1 for the x squared term. I don't have an x term, so I need to put in a 0 there. And then my constant term, negative 1 at the end. And let's go ahead and do it. You drop down the 1 and multiply by 0, that's 0. You add these guys up and that's 0. You multiply that by 0 and you get 0. And so my remainder is negative 1, but if you remember, we don't care about the remainder. This, we get to just cross off. So what we have Again, we divided x squared by x, so this is just x. All right? Or you could call it x plus 0, but you don't need to. So my slant asymptote is now y equals x. All right? So I'm going to graph both the asymptotes. And so we've got one at 0 coming straight down the y-axis here. We've got the line y equals x, so y equals x is just starting at 0, 0, slope of 1 to 1, all right, just like this. And then I'll go ahead and attach this. Here we go. All right, and everything else just goes back to the same thing. Find your x-intercepts, find your y-intercepts. So again, when I go to find my x-intercepts, I set the function equal to 0. This is x squared minus 1 over x. But again, if you're thinking ahead, you know that the x-intercepts come from the numerator. So this is really all I need to focus on is 0 equals x squared minus 1. I add 1 to both sides. That's 1 equals x squared. I square root both sides, and I get plus and minus. What's the square root of 1? It's 1. Oops. 1 equals x. So I have two x-intercepts again, positive and negative 1. And let's do the y-intercept while we're at it. We're going to do h of 0. Now again, I'm just going to use my function up top because, hey, look at that. 0 minus 1 is negative 1. But if I plug 0 into the bottom, I am now undefined. Undefined. Well, let's think about this for a second. I have a vertical asymptote right on the y-axis, which means I can't touch that. I cannot ever touch the y-axis. So I shouldn't be able to find a y-intercept. All right. So let's graph our x-intercepts then. We have one over here at negative 1. We have one over here at positive 1. And so now I'm going to just start a t-table again, and I'm going to choose some values for that. So in this case, I might try, I don't know, going to the left side, maybe a negative 2 and a negative 3. So negative 3, negative 2. Going to the right side, a positive 2 and a positive 3. Just kind of depends on what you need here, what helps you out. So at negative 3, I'm at negative 2 and 2/3. At negative 2, I'm negative 1.5. At positive 2, I'm at 1.5. Interesting how this one turns out, huh? And at 3, I'm at 2 and 2/3. All right, so let's graph these guys. Negative 3, negative 1, 2, and 2/3 right above the asymptote. Negative 2 is negative 1.5. Look at the curve on this guy. Pretty extreme on this side. So on this left side, again, we're coming up against the vertical asymptote, and then we're rolling down below the x-axis and right against the horizontal asymptote. So pretty extreme curve there. And the same thing is going to happen on the other side. 2, 1.5, and 3, 2 and 2/3. Look at how close that thing gets to there. So down against the vertical asymptote, up right against the slant asymptote, and there's your graph right there. Okay? Now, if we're talking about domain here, the domain would be x in the set of reals, x not equal to 0 here. We're not going to talk about the range on this one at this point. All right? All right. Looks like we have one more here. All right. So this time, we're going to factor again just to check. Let's see, what do we have here? Looks like I can factor an x out of the numerator and denominator. So I factor out an x, and that leaves me x squared minus 1 in the numerator. I factor the denominator, and again, I'm going to factor out an x. That leaves me x plus 2. All right? So this time we do have a whole. So the whole is coming from this factor of x, so I set that equal to 0, and I have a whole at x equals 0. The next thing I'm going to do is I'm going to take that whole and I'm going to remove that discontinuity. Okay, that's why it's called a removable discontinuity. And then I'm going to take my equation and I'm just going to factor the rest of it just to see what's going on here. X plus 1, X minus 1. Okay, so now I can see that nothing else is going to cancel out here. X plus 2. But it does show me that I have a hole at 0. And I have a vertical asymptote at x equals -2. To find the y value of the hole, I need to plug in 0 to either the red function here or the blue function after I cross off the x's. Alright? I'm actually going to plug into the blue function because it's easier, because 0 squared is 0. Take away 1 is -1. So now we're doing g of 0. So this equals -1 over, and then in the denominator 0 plus 2 is 2. So I know I have a hole at 0, -1/2. Now, I'm going to graph the vertical and the hole right away here. So vertical at x equals -2. Hole at 0, -1/2. Hey, you know what? That's my y-intercept right there. So I don't even have to worry about going to find a y-intercept on this guy because it's going to turn out to be at the hole. Alright? So I'm not going to worry about that. I do need to find my slant asymptote. So I'm going to go back up here a little bit. I need to divide x plus 2 equal to 0. So that's going to be x equals -2. And I'm going to divide that into x squared minus 1. So again, setting up my synthetic division here, coefficient of x squared is 1. There is no x term, so I need a 0. And then my constant term, -1. And I'll throw out my remainder in a minute. Drop down the 1, multiply by -2, that's -2. Add them up, you get -2. -2 times -2 is 4. But even though this turns out to be 3, I don't care about that. I get to toss the remainder. This is now x minus 2. I throw a y equals in front of it, and that is my slant asymptote. Let's go ahead and graph that. Alright, so I'm down at -2. Again, a slope of 1 to 1 makes it easy. Just up 1 over 1, down 1 over 1. There we go. Alright, so there's that guy. Don't need to worry about y-intercept because, again, there's my y-intercept. That's my hole. Okay, so I'm not going to worry about that. Find the x-intercepts. Alright, so here we go. We have 0 equals, and again, my function that I'm dealing with now is x squared minus 1 over x plus 2. I don't care about the denominator. My x-intercepts are going to come from the numerator. X0 equals x squared minus 1. Add 1 to both sides, I get x squared equal to 1. If I square root both sides, I get x equals plus and minus 1 again. Alright, let's graph those guys. So I have a, check it out here. I have a x-intercept here at 1, 1 here at -1. I can see the hole down there. I already know what the right-hand side of this graph looks like. It's going to come down. It's going to roll something around here like this, back up against the slant asymptote. That part's done. I don't need any points there. What I do need are some points to the left. And so that's what I'm going to focus on in my t-table, are points to the left of my vertical asymptote. Alright? So I'm going to choose -3, -4, and -5. And I'm going to plug those in. -3 comes out to be -8. -4 comes out to be -7.5. And -5 turns out to be -8 as well. Interesting. Alright. So -3, -8's down here. -5, -8's right over here. And -4 turns out to be -7.5. So again, you can see that the graph's coming up the slant asymptote. It's going to curve around and come back down right against a vertical asymptote. And that is how you graph a function with a degree greater in the numerator than in the denominator.